In this video, we discuss the linear approximation of a function. So let's see, for a function y equal to f of x with the graph in black, let's draw a tangent line to the graph at x0 in red. And the equation of the tangent line, as we know, is given like this. It's a straight line. Derivative at this location is a slope, so we can easily write down the equation. This tangent line function is called the linear approximation of the original function of f of x at x0. So at each location, the tangent line function is called the linear approximation of the function. What it means is this tangent line, as we can see, is very close to the function itself when we are around x0. If too far, it's not close, right? You can see the gap. It's getting wider and wider. So this whole approximation idea works only if we're not far away from x0. Okay, so this takes care of definition of linear approximation. Now, what kind of work we can actually do with this concept of approximation? Let's look at the function itself and the approximation, straight line, tangent line in red. We observe this is an enlarged graph, so we can see more details. But for this whole business of approximation to actually make sense, the delta x, which is the distance between x0 and whatever location we want to do approximation, this distance has to be small. All right, let's see. First, let's see along the function itself. So if we're going from location x0 to x0 plus delta x with an increment of delta x, right? The value changes from f of x0 to f of x0 plus delta x, x0 plus delta x here. And we see the difference is indicated, the amount of increase in the function value is indicated in black here, right? Just so we see comparison. We see along y-axis too, from here to here, but here I want to see comparison, so I mark it in black. So this indicates the amount of function increase of function value, which we can calculate, right? Just do the difference algebraically. Now let's see the change in the tangent line function when we move again from x0 to x0 plus delta x. It was here, then it's here. So the change in function value is indicated in red here. If we calculate, we can subtract the value of the tangent function from the value of the tangent function here. So we get this. Actually, we use the function here. This is the equation of the tangent line. So we evaluate this at the new location, subtract the tangent line function value, which is the same as f of x0. So we end up with this difference f prime at x0 times the change in x. Anyway, so we can see the graph. Red indicates the change along the tangent line. Black indicates the change along the original function. So black is the actual change of the function. But if we imagine delta x being small, not like this far apart, if delta x is very small, like this little bit, then the red increment would be just this, the black increment would be this. They're close, they would be close, it would be much closer. Right now, this, like I said, is the enlarged illustration of the changes. From here, we can visibly see the actual change we call the delta y in black. The change along tangent line in red is this. So we can see this is like the arrow. But then again, from this point of view, we can see if we move this new location much closer to x0 here, the difference would be this little bit. So this is the difference. As we move closer and closer to x0, the difference between black and the red is shrinking, making the approximation more accurate, or the estimate, right? So this is our first approximation result. We estimate the actual change in function value using the change along the tangent line, which is the product here. And this product is actually called differential of a function, denoted as a dy. And we'll talk about this later. All right, so this is the one result we observed, approximation result we observed. Now, let's look at the function value itself, not like an increment in function value, but the function value itself. So at this new location, the actual function value is up here, f of x0 plus delta y. I use blue color to indicate the actual function value. That's the height of the point on the graph here too. And then I use also the red to represent the value of the tangent function. Remember, it's always between original function and the tangent function. Okay, so this time I want to compare the actual function value and the tangent function value. Okay, they're not the same, and we see difference or arrow. This would be the arrow. But then again, we notice too, if we're much closer to x0, then this arrow becomes smaller and smaller. So this means we could use tangent function value to approximate original function value if the delta x, which is the distance here, is small, and that's written here. So this is the actual function value. This is the tangent function value. So now why do we do this? Well, just algebraically, at some arbitrary location, this point, this value could be complicated, like a decimal with a lot of decimal points, right? It'd be complicated to evaluate the function, at those locations and subtract. The hope is it could be much easier to just work with the tangent function. So as you can see, the results we summarized. This is just to evaluate the change using the tangent function, which is the straight line, first order polynomial function. This is basically to evaluate again the first order polynomial function. So to find approximate change of function, we use the tangent line. To find approximate value of the function value, we use the tangent line, right? Okay, assuming x0 is kind of a simple, like whole number. It's much easier to evaluate the f and f prime at this location, which are called like a good number. All right. In general, your f could be just anything. So to actually do this actual change or actual function value, pretty complicated without a calculator. But if we choose the x0 correctly, maybe much easier to just estimate change along the tangent line here or evaluate the tangent function. Okay, so these two results are summarized on this page. So from location x0 with an increment of delta x, we're at a new location. So this is shows the change in the input function in the variable. With that, we came up with these two approximation formula. This is the change along tangent line that we use to approximate the change along the original function. This is the function value of the tangent function that we use to approximate the actual function value. Okay. This product, derivative function times the change in x, is what we call in calculus differential of a function. All right. So what's a differential of a function? Differential of a function is derivative times dx. It's not the same as the derivative. It's a derivative times dx. All right. So now let's see some example. So first thing is we want to see just a very simple problem. How to find linear approximation of a function. So linear approximation of a function at a given location is, well, just the tangent line. And I already got the formula here. That's a tangent line equation of a tangent line formula. So all we need to do is to find the derivative. Here's our function. So the f prime is 2x minus 2. F prime at 1 is 2 times 1 minus 2. Derivative is 0. We need the function value. So function value is 1. Function value add 1. So we just plug in 1 square minus 2 times 1 plus 5 equal to 4, and then plug in. So the equation of the tangent line, which is our linear approximation, is, well, derivative, let's plug in, derivative is 0. So it's 0 times x minus 1 plus 4. So it's actually a horizontal line. But anyway, very simple linear approximation of a function is basically the tangent line function. Next, let's use this approximation formula to estimate value of some apparently complicated expression without using calculator. So this is to try to estimate the function value. We're going to use this formula here. So again, we're going to try to come up with a function, come up with x0, what I call the good location. Good location, good value means we can easily evaluate f and f prime. So by calculating the right side, we're going to find the approximate value. Here's there's no prime here. All right. So first thing is we need to determine a function. The function is very obvious. The expression we're trying to estimate is a cubic root. So our function naturally is cubic root of the function. And then we need to determine the x0. Now, how do we determine x0? Well, x0 should, there are two criteria to determine x0. First, x0 should be like a good number, meaning it'd be easy to evaluate the function at. So for a cubic root function, we choose to use in this problem, good numbers would be hopefully perfect third powers, because if you take a cubic root of third power, you can get an answer right away without using calculator. So that's one criteria. Other criteria is your good number. There could be a lot of good numbers. Okay, your good number should be very close to the original value of 26.9. Idea is if it's very close, the approximation is better. If your number is far away from 26.9, the error can be huge. As we can go back to the picture here. So this is a good number. This is the actual given original, right? So you want to make sure they're not too far away. If they are too far away, then the approximation is not going to be good. So with these conditions, we clearly can choose 27. 27 is a good number. We can easily take a cubic root of 27, and 27 is very close to 26.9. Okay, so once you find that your good number, now this is how you determine the delta x. Remember here, you need to find the delta x. So how do you do that? So 27, you write down first, then write down your 26.9. That's the original given number here, the actual value. Then find the difference. So always subtract 26.9 minus 27. You get negative 0.1. That is the delta x. So the given number minus the good number you pick it up, get the value of delta x. You always do that, and then you can never be wrong. Okay, so in this formula we identify the function involved, pick it up, good number x0, and calculated value of delta x. And we're ready to work on the right hand side. Always only work on the right hand side. Okay, so what do we need? We need f prime at x0. So f, let's rewrite f as a third power and then do the prime. So f prime is 1/3 x to negative 2/3 power, and f prime at 27 is 1/3 27 raised to negative 2/3 power. We put on the bottom 1/27 raised to 2/3 power. See what it is. So 27 to 2/3 power, we can do 1/3 power first, get the 3. And then square, we get the 9. So it's 1/27. F prime at the 27. And then what's f at the 27? F at the 27, we need that because here, this part. F at the 27, well, simple. That's the reason we pick up 27 in the first place. It's just 3. So we have everything. Therefore, let's write down our answer. So cubic root of 26.9 is our function this time at 27 plus negative 0.1 equal to approximately, so this is just like the left side there, equal to approximately f prime at the 27 times negative 0.1 plus f itself at the 27. Then we plug in our value 1/27 times negative 0.1 plus 3. Alright, so we just stop here without using calculator. Just a little bit less than 3. We can get the exact kind of value you could of course use a calculator to verify. Okay, so this is to use one of the approximation formula to estimate value of some expression. Now let's use the other approximation formula to estimate the change in function value. So let's see a situation. This is a word problem. Suppose the side length of a cube is measured to be 10 inches with an accuracy of 0.1 inch. Use the approximation formula or differential to estimate the maximum area in the computed volume of the cube. So what's going on here? So there's cube. Graphing is not required. I'm just drawing something to show you what's going on. So we measured. It's approximately like 10 inches, but it's not accurate. There could be more 0.1 inch more or less. All right. So we're saying. So what's the maximum error of our measurement for the volume of the cube? So it's to try to see what kind of change in volume there could be because of the error in measurement. Okay, what we do? First of all, set up the volume function. Our volume function is going to be, let's say the length of cube is x, so volume is third power. So we are trying to use the change in the volume approximation formula here when there's a change in or arrow in x, delta x. So in this problem, it's pretty straightforward. Actually, the measurement was taken when x is 10, and then the arrow in our measurement is 0.1. So according to the formula, the dv equal to v prime dx, and that's a 3x squared times delta x. Now plug in. So the 100 here, 10 squared times 0.1. So it's a 300 times 0.1, that's 30 cubic inches. All right, so this is how we apply the differential. This is actually differential of the volume to estimate the error in volume when the error in the side is 0.1. In other words, with this kind of measurement, right? We say the side length is about 10. Therefore, the volume is about 1,000. So what's the error we're talking about here? The error could be just 30 cubic inches, because our measurement could be 0.1 more or 0.1 less. So you can add the 30 to your estimated volume. No, 1,000. What's 1,000? So it could be plus or minus 30. All right. So let's stop here.